Okay, thank you. So I'm going to talk about how to build differential characteristics in ARX designs. So it's, of course, related to previous talks about differential attacks also. So if you look at what we have in symmetric key cryptography, you can see that there are many different ciphers, and they don't all look the same. And for instance, here is small present, here is free fish, and you can see they look really different. They don't use the same operations. And more generally, we define two main families of ciphers. One of them is what we call SPN, and for instance, the AS is from this family, and the main idea here is that we use S-boxes, so we have layers of S-boxes and then linear layers. And when you combine them, the S-box gives a good amount of nonlinearity, so when you do one round like this, you have a good amount of nonlinearity, a good amount of diffusion and confusion. And so you repeat this for a number of rounds, and you get something that is expected to be quite secure. Now, on the other hand, the ARX family is completely different. Here, we only use very lightweight operation. We just use additions on 62-bit words or 32-bit words. We use rotations, and we use XORs. And all those operations are very simple, and they are very efficient in software and very efficient in hardware. This is an idea that's inspired by the MD and SHA family of hash functions. And now what you do is that you have all those very simple operations, and you do very lightweight rounds, and you do a large number of them. And this is expected to also give a good security. So this ARX idea is now very popular, and we have many designs using this. We have hash functions, stream ciphers, block ciphers, PRF. Everything we can do in symmetric crypto, we can do it with ARX. And actually, some of the most efficient designs we have now are based on this important idea. Now, we think that ARX is secure because we're mixing operations which are basically incompatible. Some of them are bitwise linear, the rotation and the XOR, and some of them are linear over modular integers. So they belong to two different words, and when we mix them, we get something that we don't have a single theory to analyze them. Now, a very important question about those ARX design, of course, is how secure are they, and how many rounds do we need to make something secure? And that's the main topic of this talk, how to analyze those ARX designs. And more precisely, we're going to look at hash functions, and we're going to look at differential attacks against ARX hash functions. So to give a little bit of background, we can look at the recent attacks on the MD and SHA hash functions. So in 2005, we had very strong attacks on MD5 and SHA-1, and those attacks are collision attacks based on differential cryptanalysis. So how do those attacks work? Well, the main idea is, so it's differential cryptanalysis. So you take a pair of inputs, you fix some difference, and you look at the difference inside the state of the function during the computation. So we're going to start with a zero difference in the state, and at some point, you will get a difference coming from the message, and then you have to track the difference inside the state, and you look at each step, you try to get a given difference. And then you want the last message difference to cancel the state difference, and then you get a zero difference again. And this is how you get a collision. You start from a zero difference, you end with a zero difference, and you get something a bit messy in the middle. So this is actually the most important part of the attack, finding those very specific differences. And then finding actual message pairs is usually relatively easy because we have lots of degrees of freedom in a hash function attack. So initially, those attacks were based on differential trace built by hand. So it's a very technical thing to do. It really takes a lot of time. It's very painful to build those trails. And the problem is that when you have one of those trails, say you have an attack on SHA-1, it's very hard to apply it to a different function because you have to do all this work again. You have to take this new function and try to build this new trail by hand. Another problem is that some of those attacks turned out to be invalid, so there's also a bit of a problem here, but really those attacks are so technical that it's hard to understand them. Now, after those initial results, there was a lot of work in trying to understand those attacks and trying to improve them. And an important line of research was try to build those differential paths automatically, try to build algorithms for this. This is something that has been quite successful for those MD and SHA hash functions, and we had a series of results giving algorithms for various hash functions. So thanks to this, we can now analyze those designs much more easily. And if you look at a different function, which is, say, very similar to SHA-1, you can use the SHA-1 algorithm, maybe tweak it a little bit, and then running it on your new design, and you will get some interesting results. So that's really the benefit of doing this automatically. The second benefit is that now you can also try to build differential paths that are tweaked to some very specific properties. So you can find trails with specific properties, and that will help you give attacks that go further than just collision attacks. So this has been used to attack mags. This has been used for attacking certificates, like in the flame attack that we've seen earlier today. It has also been used to attack combiners. And so the main point is, once you get this automatic construction, you can really do a lot more work on those functions. So it's really important to do this. Now, if we go back to ARX functions, the situation is a bit similar. If you want to do differential cryptanalysis on those functions, you also have to do all this heavy work of looking at all the bits in the state and building those differential trails one bit at a time, deciding if you will put a difference or not put a difference. And that's, again, a very, very hard process to do. So what we want to do in this work is to give an algorithm that would do this automatically, and then we hope that we will get the same benefits as we got in the MD and SHA case. So how do we do this? Well, the main setting is we're going to look at hash function attacks. And in this setting, the differential trails that we are interested in, we can build them from two sections that will be high probability sections. So we can build them by hand. They will be very simple trails with only a few active bits. And what we want to do is connect them. So we want to build this red part here. So we are given something at the top, something at the bottom, and we want to go from one to the next. So this middle section will be very complex. It will probably have a pretty low probability. But in the case of hash function attack, it's not too bad to have a low probability because we can use degrees of freedom to avoid it. So it's not really a problem. Now, if we succeed to build this algorithm, the way we're going to use it is that we would build those input and output difference by hand on the key difference, and we select them so that we have nice high probability trails at the beginning and at the end. And then we run the algorithm in the middle, and it will find these very complex trails in the middle. And afterwards, to finish the attack, we will have to find a pair of values, but this will be easy because we have lots of degrees of freedom, and the trails are pretty nice. So how do we build this kind of algorithm? So we're going to do something very similar to previous work on the MD and SHA hash functions. And the main idea is we start with those trails which are given as simple trails with high probability. And in the middle, initially, we say, well, we don't know anything about those values here. So we're going to try to learn information about this. And the first step is to propagate the information that we have already. So we have some information here. We have the difference at the beginning of this trail, and we can propagate some information to know something after one round. If you know the initial difference, after one round, you can still know something about this difference. And that's what we do here. Now, we can get some information, but of course, we will not get everything. So the next step is to guess something in the middle. So we just pick one bit, and we say, OK, this bit will be active, or OK, this bit will be inactive. And once we do this, we have some more information in this system, so we can run the propagation again, and we will get some new information, and then we repeat this. We guess something, we propagate, we guess something, we propagate. And the hope is that at the end, we will get something where everything is known, and this will give a valid characteristic. So of course, it will not work all the time. Sometimes we will end up with a contradiction, so we have to go back and do some backtracking and restart from some of the guesses. So in our case, we use a few extra tricks to make this work better on those ARX designs. And the first one is that we specify in advance where we will do this guessing. So we will select a few words in the middle, and those will be the one where we do this guessing. And we will always do the guessing in the same order. We will always guess the bits from the least significant to the most significant. And thanks to this, what we can do is when we realize that some choice doesn't work, that we're going to fail, we can stop at some point, and we can remember the best choices that allowed us to go the further. And then we can restart from this choice and try to modify it a little bit, and then we can use some kind of optimization algorithm, and what we do is basically simulated annealing. And thanks to this, we can eventually find characteristics that do work for some number of rounds. So in this algorithm, a very important step is the propagation algorithm. And I'm going to talk a little bit about it. So the main idea is that we look at some operation, for instance, an addition, and we assume that we know some information at the input. So for instance, if this is the first round of our characteristic, the initial difference is given as an input to the algorithm, and now we try to propagate this information to learn something in the middle. So if we do this in a bitwise fashion, it's not going to work very well, because once there is an active bit, all the higher bits, we don't know whether they're active or not, because there might be a carry, and if there is a carry, all those bits will be active, but if there is no carry, those bits are inactive. So if we just look at the bits one by one, we can't say anything useful about them. So this propagation will not go very far, and we are stopped very early. So in previous work, what they do is then they guess whether there will be a carry or not. But in our case, we would like to avoid this so that we can propagate as far as possible without making any guess. So what we use instead is multi-bit constraints, which have been introduced at last Asia Crypt. And the idea here is that instead of looking at a single bit at a time, we look at 2 bits simultaneously. And when we do this, when we are inside this carry chain, we can say something about those bits. Because if we look at 2 bits simultaneously, they can both be inactive if the carry chain stopped earlier. They can be both active if the chain goes past those bits. Or the last possible situation is that the least significant bit is active and the higher one is inactive if we are just at the end of the chain. But it's impossible to have the low bit inactive and the high bit active. So we can eliminate some candidates, and that's how we can propagate more information. Now we know something about those bits. We don't have a lot of information, but we have some information. This will really help the algorithm to propagate further. Another important thing in those attacks is the idea of degrees of freedom. And here the main observation is that if we just look at a fixed permutation, if we don't have any key addition in the section where we do this connection, it's probably not going to work because we're fixing some arbitrary difference at the top, some arbitrary difference at the bottom, and those differences, they're not chosen so that they are compatible. They're just basically arbitrary. So what we expect is that on average there is a single pair that will satisfy those differences, and the single pair is not going to be useful for a differential attack. So we need to have some key addition, some degrees of freedom in the middle. And the way we use them is that we're going to do the guessing just before and just after this key addition. So the bits where we do the guess are just before, just after the key, and this will allow the algorithm to pick some conditions on the key and to select some subsets of the key for which it will be able to build those trains. So those are the main ideas of the algorithm. Now I'm going to go to the applications that we did. So we looked at skein. So skein is a hash function that was one of the SHA-3 finalists. So it's a pretty solid design. It has been well studied. And of course, it's an ARX design, so it uses addition, rotation, XORs. And the network looks like this. So when we want to apply our tools to skein, the first step is to select a model for the attack. What kind of attack are we going to look for? And the most obvious one will be to look for collisions. But before we can look for collisions, we're going to do something a little bit easier. That is semi-free start collision. And in a semi-free start collision attack, what we do is that we allow to select some chaining value that will be easier than a random chaining value. And in the case of skein, the chaining value is used as the key because it's using MMO mode. And now what we do, so we want to have a fixed chaining value, so we don't have any key difference. So this means that we must have a trail which is active for all rounds. And what we do is we want to have the difference at the top and the difference at the bottom to be the same so that they cancel in the feed forward. And that's how we get a semi-free start collision. And now to run the algorithm, we select some difference delta, which is very sparse. Then we build those two very simple trails with only a few active bits. And then we run the algorithm on the red section to build something to connect them. It turns out that it works pretty well on skein. And we can build those characteristics for 12 rounds. And we have a practical attack where we can actually find pairs of messages that gives semi-free start collisions. So that's a good thing. It actually works. The bad thing is that the paths are not that good. They are actually pretty dense, so they have a relatively low probability. And more importantly, we have many conditions on the key. So this means that those trails are only valid for some subsets of the chaining values, and that's why it's hard to build a collision attack out of them. So we can still try to build a collision attack. And what we do is we build a lot of characteristics like this, with many, many, many characteristics, and each of them is valid for subsets of the chaining values. And we have all those subsets, and we use a kind of meet-in-the-middle approach, where first we build all those subsets, and then, starting from the actual IV, we use random messages, and we try to reach one of those subsets. And if we do this, what we get is a collision attack for the hash function skein, well, reduced to 12 rounds, and the complexity is about 2 to the 100. So this is nice because it's really an attack on the full hash function. It's not some weak distinguisher on the compression function. But of course, the number of rounds that we can reach is pretty small. Now, since everything is automated, we can also look at other settings. And in particular, we can look at free start collisions. And in a free start collision, what we do is that we allow to have 2 different chaining values. And when we do this, we can have a difference in the chaining values. And this allows to have blocks of rounds which are inactive. Then the difference will come from the chaining value, which is used as the key here. So thanks to this, we can add more rounds because we have blocks of rounds completely inactive. So those don't count, those don't cost anything. So we can go further in our attacks. And in this case, it turns out that we are actually very lucky because the key schedule of Skein is very nice with us in this attack. Because if we put some difference in the chaining value, we will have some difference at the beginning, and it turns out that 20 rounds later, we get the same difference because the key schedule repeats after 20 rounds. And 20 rounds is exactly the number of rounds we can reach. And because this difference at the top and at the bottom are the same, they will cancel in the feed forward. And so this allows to give a real free start collision attack on the compression function. And again, the construction of this middle section works relatively well, and we can run the algorithm, it works, and then we can find a pair of messages, and everything works as expected. So to conclude, the main result of this work is that we can automatically build differential trace for ARX functions. And the main ingredients we use are those multi-bit constraint, the fact that we guess bits in the middle at a fixed position, and this simulated annealing that comes from this. So we applied this to Skein 256, and the main results are a collision attack for 12 rounds of the hash function, and semi-free start and free start collisions for the compression function. And all this actually shows that there is a huge security margin in Skein because the full version has 72 rounds, and we are very, very far to break this. So all the code for this is available, so please use it, and we hope that this will be useful to evaluate the security of various ARX designs. And thanks for your attention.